In 2022, deep in a remote Australian rainforest, a researcher watched a tiny ant get launched into the air with the speed of a projectile fired from a crossbow. The observer had no idea what he had just witnessed. It took years of investigation, a dedicated research team, and a formal study published in Current Biology to explain that single rapid-fire event. What they uncovered is a creature small enough to sit on your fingernail, armed with a mechanically sophisticated weapon system. We usually picture spider webs as simple, sticky nets, passive traps that an insect eventually stumbles into by pure bad luck. This spider operates on a different principle. It uses silk to construct a mechanical weapon system designed for high-velocity interception. Scientists named it the Ballista spider. The name comes from the ancient Roman siege weapon that stored tension in twisted cords and released it all at once to launch heavy projectiles. The name is literal. A team led by Professor Ajay Narendra at Macquarie University confirmed this arachnid is assembling the same mechanical device. This is macro-level engineering applied at a scale you would need a microscope to fully appreciate. The spider spins up to 60 taut silk lines to form an upside-down cone. Sitting at the top, it holds the gathered lines under intense strain. It maintains tension until a target makes one mistake, biting the baseline. This web is a kinetic energy battery, remaining primed until the moment it discharges. The only target meant to trigger this trap is the green tree ant, and the Ballista spider hunts nothing else. The second the ant bites into that bottom silk line, the spider releases the tension from above. All those tightly pulled lines snap back simultaneously. The launch propels the ant more than a foot through the air, directly into the spider's main web. This happens in a fraction of a second, exerting roughly 140 times the force of gravity on the ant. Before the insect can process that it is under attack, the trap's mechanics overwhelm it, neutralizing a fast-moving target with sudden, extreme force. Comparing biological catapults, the slingshot spider pulls its web into a cone, but uses its body as the launch mechanism, limiting force to its own muzzle strength. The Ballista spider externalizes this workload, storing energy entirely within the silk structure itself. Removing its body from the mechanism allows the trap to hold and release far more force than the spider's legs could ever support. Why go through all this engineering trouble just to hunt a single species of ant? Because the green tree ant is dangerous. They have a powerful bite, they can spray acid, and they live in coordinated colonies that can reach 5 million individuals. If a tiny spider tried to grab one of these ants directly, it would risk alerting the surrounding swarm, provoking an entire army to attack. The catapult acts as a stealth mechanism. It picks off a single, isolated ant from a safe distance, removing it from the environment before the rest of the colony notices. This is a strategy for asymmetrical warfare, a zero-risk assassination tool built for dangerous territory. This behavior is a calculated risk mitigation strategy, encoded entirely into a few strands of silk. Humans built the Ballista 2,000 years ago and have spent centuries refining stored tension weapons. Evolution reached the same mechanical conclusions by testing thousands of failed designs until one finally worked. Tension storage, trigger mechanisms, force multiplication, and safety at a distance. This microscopic organism solved every one of those engineering problems without a single blueprint. Complex arrays of physics operate in silence on the rainforest floor, showing how much mechanical sophistication can exist in a creature smaller than a fingernail. If you want more videos exploring these biomechanical for hands, subscribe.